See, in the previous session we have discussed about ethers, classification, IUPAC naming system, common naming system, followed by synthetic methods. In the synthetic methods we have discussed Williamson's reaction. Yes, in the Williamson's reaction, what happens? Alkyl halides upon reacting with sodium alkoxide forms ethers. Yes, we have discussed about the limitations also. Yes, so in this session let us discuss the application of Williamson's reaction for the synthesis of phenolic ethers. What? For the synthesis of phenolic ethers. Okay. The phenolic ether example is anisole. Yes. So we are going to discuss about the preparation of anisole using what? Williamson's reaction. So let us see what the reaction is. See, the alkyl halide, any alkyl halide upon reacting with sodium phenoxide, upon reacting with what? Sodium phenoxide. This is sodium phenoxide. This is alkyl halide. That is specifically, if you want, I will write just this methyl by methyl bromide. That is alkyl halide instead of alkyl halide. So that is methyl bromide. Methyl bromide upon reacting with sodium phenoxide. See here, O minus and Na plus. The phenoxide ion attacks this electrophilic carbon and bromide leaves out. Combines with what? Na plus to form NaBr. Okay. See here, O minus attacks what? This carbon atom, that is methyl carbon atom, to form CH3 plus NaBr. So this is anisole, or what? Another name for this one is what? This is methyl. This is phenyl, methyl phenyl ether. Methyl phenyl ether. So IUPAC name for this compound is what? See. So this is larger group and methyl group is smaller group. We are choosing the benzene as a parental hydrocarbon and we are introducing alkoxy for the what? This methyl group. Therefore the IUPAC name is, see, small group is what? Methyl. Therefore methoxy, and the larger group is benzene. So IUPAC name is what? Methoxybenzene. Methoxybenzene. Okay. See here, sodium phenoxide upon reacting with methyl bromide forms anisole. Okay, sir. ಈ ರೀತಿ ಮಾಡಿದ್ರೆ ಹೆಂಗಿರುತ್ತೆ ಸರ್? ನೋಡಿ ಸರ್, ಇಲ್ಲಿ ನಾವೇನು ಮಾಡ್ಕೊಳ್ಳೋಣ? ಬ್ರೋಮೈಡ್ ತಗೊಳ್ಳೋಣ ಸರ್, ಕ್ಲೋರೋಬೆನ್ಜಿನ್ ತಗೊಳ್ಳೋಣ ಸರ್, ಕ್ಲೋರೋಬೆನ್ಜಿನೋ ಸರ್. ಇಲ್ಲಿ ನಾವು ಮೀಥೈಲ್ ಬ್ರೋಮೈಡ್ ಬದಲು ನಾವು CH3ONA ತಗೊಳ್ಳೋಣ ಸರ್, ಅಂದರೆ ಸೋಡಿಯಂ ಮೆಥಾಕ್ಸೈಡ್ ತಗೊಳ್ಳೋಣ ಸರ್. ಈಗ ರಿಯಾಕ್ಷನ್ ಆಗಲ್ವಾ ಸರ್? ಈ ಥರ ಇದ್ರೆ ಅಂದರೆ ಏನಾಗುತ್ತೆ ನೋಡಿ, ಓದಿದ್ದೀವಿ ನಾವು ಏನಂತ? ದಿಸ್ ಈಸ್ ಅರೈಲ್ ಹ್ಯಾಲೈಡ್. What is this? Aryl halide. Aryl halide, yes. So here CH3O minus and Na plus. This is methoxide. This ion is what? Methoxide. Yes, this methoxide is a nucleophile. Methoxide is a what? Nucleophile. We know that alkyl halides doesn't undergo nucleophilic substitution reaction easily. We have discussed the reasons also, because there is a double bond character between this carbon atom and the halogen atom, and the carbon atoms in benzene ring is sp2 hybridized, therefore it is less polar in nature, and repulsion between the benzene ring and the approaching nucleophile, instability of phenyl cation. We have discussed all these reasons in the alloarins unit. Yes, so here also this is aryl halide is not a good substrate for the synthesis of what? Anisole, because aryl halides doesn't undergo nucleophilic substitution reaction easily. Okay, and see, therefore it doesn't yield anisole. Doesn't yield what? Anisole. Remember this point. Williamson's ether synthesis for the preparation of what? Anisole. Okay, so alkyl halide reacts with what? Sodium phenoxide to form anisole. Okay, remember. See, the next method of preparation of ethers is from the dehydration of alcohols. We have discussed in the introduction class of ethers, that is, ethers are also called as anhydrides of alcohols. That means ethers can be obtained by the dehydration of alcohols. Yes, see, here we take an example of our ethyl alcohol, that is C2H5OH plus, for simply purpose I am writing inverted fashion, C2H5, ethanol. This is also ethanol. We have discussed this reaction in the chemical properties of alcohol, that is reaction of ethyl alcohol with concentrated sulfuric acid at different conditions. See, here concentrated sulfuric acid, temperature is very important, temperature specific reaction, that is, it is temperature is around 140 degree Celsius, 140 degree Celsius. At this condition, two molecules of ethyl alcohol react with each other with the removal of water molecule H and OH combines to form what? H2O, and remaining thing you write it as such, see, C2H5O, and here this side C2H5. This is two ethyls are there, that is diethyl ether. IUPAC name is, that is ethoxyethane. IUPAC name is ethoxyethane. Okay, so this is one method, that is dehydration of alcohol. Okay, another method is there still. See, third method is from alkyl halides. Okay, see, from ethyl bromide, see, ethyl bromide C2H5Br, okay, upon reacting with, just I write one more molecule, see, C2H5Br, upon reacting with dry silver oxide, upon reacting with what? Dry silver oxide. Upon reacting with dry silver oxide, see, there are how many silver atoms are there? Two silver atoms. These two silver atoms combines with these two. This is one bromine atom, this is another bromine atom, to form what? AgBr. And see, we left is what? C2H5. From the silver oxide, O, insertion of oxygen between two alkyl groups has taken place, C2H5. See, again that is the same thing, diethyl ether or ethoxyethane. See, from ethyl bromide upon reacting with dry silver oxide, this is very important. What? Dry. If we use moist silver oxide, wet silver oxide means Ag2O in water. Ag2O in water forms what? Silver hydroxide. AgOH. OH minus is a nucleophile. So, if we use moist silver oxide, the bromide is replaced by hydroxyl group to form ethanol. But in case of dry silver oxide, it forms what? Ethers. Remember this thing. Ethyl bromide upon reacting with dry silver oxide, forms ethers. Okay. If ethyl bromide reacts with moist silver oxide, it forms alcohols. Okay. Don't confuse. Moist is different. Moist silver oxide yields alcohols. Dry silver oxide yields ethers. Okay. See these reactions. Okay. So, synthesis of ethers is from three methods, that is up to now we discussed. That is, one is Williamson's reaction, second method is dehydration of alcohols, and third one is from ethyl bromide. Okay. See, after the completion of the synthetic methods of ethers, let us discuss about the structure of ethers. See, that is I am taking an example of dimethyl ether. Or ethoxyethane. See, the oxygen atom of ethers, either it may be dimethyl ether, diethyl ether or any ethers, the oxygen atom is sp3 hybridized. sp3 hybridized. That is, sp3 hybridization means there are, how many hybrid orbitals are there? There are 4 hybrid orbitals are there. Yes, among these 4 hybrid orbitals, in ethers, the oxygen atom is having how many lone pairs? 2 lone pairs. Yes, the oxygen atom is having what? 2 lone pairs. Among the 4 hybrid orbitals, the 2 hybrid orbitals and 2 hybrid orbitals. See, the lone pairs of electrons occupied the 2 hybrid orbitals. The lone pair occupy what? 2 hybrid orbitals, and the remaining 2 hybrid orbitals of oxygen atom, one hybrid orbital overlaps with the carbon atom of the alkyl group to form a sigma bond, one sigma bond. Similarly, another hybrid orbital of oxygen atom overlaps with another carbon atom of the alkyl group to form another sigma bond. Okay. See, the oxygen atom in ethers is sp3 hybridized. In sp3 hybridization, there are 4 hybrid orbitals. Among the 4 hybrid orbitals, 2 hybrid orbitals are occupied by the 2 lone pairs of electrons. How many lone pairs of electrons are there on the oxygen atom? See, this is one lone pair and this is another lone pair. The 2 lone pair of electrons are occupied by the 2 hybrid orbitals, and remaining 2 hybrid orbitals, see, one hybrid orbital of the oxygen atom, that is sp3 hybrid orbital, overlaps with the carbon atom of the alkyl group to form one sigma bond. Similarly, another hybrid orbital of the oxygen atom overlap with the other carbon atom of the another alkyl group to form another sigma bond. We can able to see here, there are 2 sigma bond. This is one sigma bond and this is another sigma bond. Okay. And the structure, this tetrahedral arrangement. The structure is tetrahedral arrangement. But remember, in case of sp3 hybridization, the structure is what? Tetrahedral, and the usual bond angle of tetrahedral is 109 degree 28 minutes. Yes, but in case of ethers, that usual 109 degree 28 minutes is not there. That is, see, in case of dimethyl ether, see, in case of dimethyl ether, the bond angle is, see, the bond angle is 111 degree 7 minutes. Okay. but usual tetrahedral bond angle is 109 degree 28 minutes. Sir, why the bond angle is deviated in case of ethers means, see, it is methyl group. Yes, it is also what? Methyl group. Due to repulsions between the methyl group, that tends to make some far away from each other. Therefore, the bond angle is increased, that is 111 degree 7 minutes because of what? Repulsions. Sir, if instead of methyl, if ethyl group is present means what will be the bond angle? See, methyl group, ethyl group. Among these two groups, which one is larger group? Ethyl group is the what? Larger group. In larger group, the repulsions are less or high. In the case of larger groups, repulsions are more. Repulsions are what? More. Repulsions are more, and as consequently what it affects, therefore consequently the bond angle is also more. See, if we instead of methyl group, if we have ethyl means there is more repulsions. More repulsions causes the bond angle also more. Okay. See, remember, in case of water, the hydrogen is small atom. Yes, what will be the bond angle in case of water molecule? That is 105 degree Celsius. Sorry, 105 degree. Yes, it is explained based on VS-EPR theory, that is because of the valence shell electron pair repulsion theory. Yes, lone pair repulsion is greater than lone pair bond pair repulsion greater than bond pair repulsion. Yes, see, in case of water, the groups, that is hydrogen atom is small atom. Therefore, the repulsion is less between these two hydrogen atoms. Therefore, the bond angle is also less. When these hydrogen atoms are replaced by methyl group is a larger group when compared to hydrogen atom. Therefore, repulsions are more. Therefore, bond angle is how much? 111 degree 7 minutes. If instead of methyl, if we have ethyl, there is more repulsions that affects also, that is bond angle is also more. If we have propyl, yes, propyl means CH3, CH2, CH2. The repulsions are more and directly it influences on the bond angle is also more. In simple words, bulkier groups increases repulsion among themselves, making the bond angle also high. Okay, that is very important point. Please remember, they may ask in the competitive exams, they give some ethers, that is dimethyl ether, diethyl ether, dipropyl ether, dibutyl ether. Arrange these ethers in the decreasing order of their bond angle. Remember, decreasing means from the highest to lowest. Among these four ethers, that is butyl, propyl, ethyl and methyl, which is bulkier group? Butyl is bulkier group. Therefore, repulsions are more and bond angle is also more. Therefore, the first is dibutyl ether is having bond angle is greater than that of dipropyl ether, followed by diethyl ether, followed by dimethyl ether. Okay, remember this point. And see, dimethyl ether or ethers have bent molecule. What? Bent molecule, that is V-shaped molecule, bent molecule. Therefore, they are polar in nature, that is they have definite dipole moment, mu is greater than 0. They are polar in nature. Okay, remember these things. Structure of ethers, the oxygen atom in ethers is sp3 hybridized. Remember, this is for 1 marks. It is very important. What is the hybridization state of oxygen atom in ethers? 1 marks question. What is the hybridization state? It is sp3 hybridized. We have studied in the first PU That is, in the sp3 hybridization, there are 4 hybrid orbitals are there. Yes, there are 4 hybrid orbitals are there. Among these 4 hybrid orbitals, 2 hybrid orbitals are occupied by the 2 lone pair of electrons of oxygen atom, and remaining 2 hybrid orbitals, 1 hybrid orbital of oxygen atom, 1 hybrid orbital overlaps with the carbon atom of any alkyl group, forming what? Sigma bond. Similarly, another hybrid orbital overlaps with the another carbon atom of the another alkyl group to form what? Sigma bond. And remember these things, the increase in the carbon atoms or bulkier the group, more will be the repulsion and the bond angle is also more. That is very, very important. And ethers have bent molecule, they have a dipole moment that is greater than 0. Okay, they are polar in nature. Okay. See, after the structure of ethers, let's move on to the next topic, that is physical properties of ethers. See, physical properties of ethers, the first point we are going to discuss in all the physical properties of organic compounds is physical state. See, we know that lower members are gases, some higher members are liquids, and still higher members are solids in nature. Here also the same trend follows, but here dimethyl ether and methyl ethyl ether are gases and higher members, that is from the diethyl ether and dipropyl ether, etc. are liquids. The liquids with a characteristic odor, that is ether odor, and they are volatile in nature. That is very, very important. They are highly volatile. Highly volatile means they have less boiling point. See, next point what we are going to discuss is the boiling point. Comparison. Let's compare the some related concept of organic compounds with ethers here. See, alcohols have higher boiling point. Yes, because of the formation of what? Hydrogen bonding. Here, in case of ethers are highly volatile because of the absence of hydrogen bonding. That is, absence of intermolecular hydrogen bonding. We have discussed in the alcohols. Alcohols have higher boiling point because of the formation of what? Hydrogen bonding between one molecule of alcohol with the another molecule. Yes, but in case of ethers, the hydrogen bonding cannot possible because of what? In ethers, the hydrogen atom is not there attached to the electronegative atom like oxygen, nitrogen, fluorine, etc. But in case of alcohol, the hydrogen atom is attached to the what? Electronegative atom, oxygen. See here, in case of alcohol, see, this hydrogen atom is attached to the what? Electronegative atom. But in case of ethers, this is not like that. See, where is the hydrogen here? No hydrogen. Therefore, intermolecular hydrogen cannot be seen in case of what? Ethers. In case of what? Ethers. Sir, even though they doesn't exhibit, they doesn't form intermolecular hydrogen bonding, they have in liquid state and they have some boiling point. Yes, ethers have boiling point, that is low boiling point, that is it may be from 31 degrees, 36 degrees or 40 degrees, 45 degrees, etc. Why, sir? What is the force responsible for this? Means there is a weak dipole forces are present. Weak dipole forces between one molecule of ether and another molecule of ether. See, weak dipole forces are responsible for the boiling point of ethers. There is no hydrogen bonding. This is very, very important. See, for 1 marks question, ethers have lower boiling point than corresponding alcohols? Why? Means answer is very simple. In alcohols they have intermolecular hydrogen bonding, but in case of ethers they doesn't exhibit or they doesn't form hydrogen bonding. Therefore the boiling point is less in case of ethers. Okay, remember this point. The boiling point of ethers is due to the weak dipole-dipole forces, and absence of intermolecular hydrogen bonding makes the ethers should have low boiling point. Okay, and the next point is the solubility. See, lower members of ethers are soluble in water, but higher members of ethers cannot soluble. The same explanation has been discussed in the alcohols also. See, lower members, the solubility is due to the formation of hydrogen bonding. Formation of what? Hydrogen bonding. See, with water here, formation of hydrogen bonding with water. It is very important. See, this is one molecule of ether, this is another molecule of ether. In between ether molecules, see, this is water. See, this hydrogen atom of water is having what type of charge? Partial positive charge. Here also partial positive, and the oxygen atom is having partial negative charge, and the oxygen atom is electronegative. That is, see, this is electronegative atom and this is electropositive. They have some force of attraction between the oxygen atom of ether and the hydrogen atom of water molecule, that is hydrogen bonding, that makes the ethers are soluble in water. Soluble in water. Lower members of ethers are soluble in water, but higher members cannot. That is, the solubility decreases with increase in molecular masses. Okay, remember this thing. These are the important points in the physical properties of ethers. This is 1 marks, very important, and here also it is 1 marks is very important, solubility. Okay.